right. So um, the fourth exam, Wednesday. Okay, that's the last day, our last final meeting. And make sure your webcam is working before the exam, before you come to class. We haven't had any problems with it, but do make sure before you come that it is indeed working. So the exam will cover sections 6.1 to 6.8. The Chapter 6 summary describes really the 8 questions that will be covered. Okay. So I hope you all got a chance to take a look at it. So we went over 2 types of line integrals. Okay. So for a given curve C, given by parametric function r of t for a less than or equal to t less than or equal to b, there's the scalar line integral, and then there's the vector field, the work-related line integral. And this is the way it's typically denoted, the scale integral. This is the way it's typically denoted, the vector field line integral. And the way it's evaluated is like this and like that. Okay, so here are the first 2 questions that you will encounter. Okay, one calculation, straight calculation of a scalar line integral, and one straight calculation of a work-related vector field line integral. So one question. Okay, so one question, calculate a scalar line integral. Okay, so that was from chapter or section 6.2. So there's a bunch of them in the exercises that we went over. Let's do a couple of them now. In a lot of these, you are asked, the curve C is described and R is not given. In some of these, the curve R is actually given. Okay. I mean, the curve is given in terms of a parameterization. Here, you don't have a parameterization. I'm planning on asking you, at least once to pick your own parameterization. So let's look at number 47, for example. So example number 47, 6.2. So calculate the line integral over C of x y to the 4th where C is the right half circle of radius 4, traversed in the clockwise direction. Now, with the scalar line integral, that actually doesn't matter. But so we'll just not consider that. So xy to the fourth ds, where C is the right half circle of radius 2. Okay, so the first thing you need to do is, pick some r of t. There's different ways to do the circle. Okay, for example, you could do r of t equal to 2 cosine t, comma 2 sine of t, essentially the definitions of sine and cosine, for minus pi over 2 less than or equal to t less than or equal to pi over 2. So that's one way you can do it. So let's take a look at that and see if that works out nicely. Okay, so you need to calculate r prime of t for the scalar line integral and the length of r prime of t. So this is equal to, for r prime of t, minus 2 sine of t to cosine of t. And so the length of r prime of t is just 2. Right? I mean, it's the square root of this squared plus that squared. So 4 sine squared t plus 4 cosine squared t, which is 4 sine squared t plus cosine squared t. All right, this is 1, so square root of 4, which is 2. Okay, so the line integral over C of xy to the fourth ds is the integral from minus pi over 2 to pi over 2 f of r of t, r prime of t dt. Okay, so f of r of t, right, we have the function xy to the fourth. X is 2 cosine t. Y to the fourth is 16 sine to the fourth t times the length of r prime, which is 2, dt. Okay, so 4 times 16 is 64 minus pi over 2 to pi over 2. Cosine t sine to the fourth t dt. Antiderivative here, let u equal, make this a little bigger, let u equal sine of t, so du over cosine of t is dt. So then this is 64 times the integral from t equals minus pi over 2 to t equals pi over 2 cosine t u to the fourth du over cosine t. So now that cosine t goes away, cancels out there. So this is equal to 64. Now let's change t here into u. So when t is minus pi over 2, this is negative 1. And when t is pi over 2, u is equal to 1. Sine t is equal to 1. So 64 u to the fourth du from negative 1 to 1 for u. So that's 64 over 5 u to the fifth from minus 1 to 1. So that's 128 over 5. So that's one parameterization you can pick, to calculate that. Another parameterization you can pick, since it's a half circle, you can do this. So there is a different choice. would be r of t equal to, well, you let y equal t, and then r of t to be the x-coordinate for the circle, right? Would be, well, to use, let's see, y is equal to square root 4 minus x squared, right? So y equal to t, x equal to 4 minus t squared, like that. So then r prime of t is equal to minus t over square root 4 minus t squared and 1. So the length of r prime of t, well, again, it's going to be equal to 4, but, let's check it out here. So t squared over 4 minus t squared plus 4 minus t squared over 4 minus t. Oh, no, it's not. I'm sorry. So this is equal to t squared plus 4 minus t squared, which is 4, over 4 minus t squared. So you have 2 over square root 4 minus t squared, like that. All right, so that would be a second way to do it. And then fxy, let's was x y to the fourth. So f of r of t is equal to, well, x is this, y is that. So square root 4 minus t squared times t. So the integral over c, xy to the fourth ds is equal to the integral. Oh, what's the range for t, the domain for t? The domain for t is minus 2 to 2. Like that. Okay, so that's integral from minus 2 to 2 of this, t times square root 4 minus t squared, 2 over square root 4 minus t squared dt. Those cancel out, and you get the integral from minus 2 to 2 of 2t dt. So that's just t squared from minus 2 to 2. So 4 plus, hold on a second, what happened? Oh, y to the fourth, x y to the fourth. It's t to the fourth. So t to the fourth, like that. So 2t to the fourth. So that's going to be equal to 2/5 t to the fifth from minus 2 to 2. So that's 2/5 times 32 minus 32, which is 64 times 2, 128 over 5. Okay, so the parameterization doesn't matter. As long as you pick one that accurately represents the curve, you're fine. Okay, one type of question. A second type of question calculate a work-related vector field line integral directly, right? By directly, I mean not using the fundamental theorem of calculus for line integrals, for conservative vector fields, I guess. Or Green's theorem. Now, I'm not going to give you a problem by which you could, calculate using the fundamental theorem or Green's theorem. Okay, I'll give you one that, essentially you can't apply them, so the only thing you can do is just calculate it directly. So there's plenty of examples in here for this. Let's take a look here. So 53, I think we did that one. So 57, now is that, I believe this one is conservative. So let's see, x, y, z, with respect to x is that. Yeah, that one's conservative in 57, so we don't want to do that one. That one is conservative as well in 59. No, it isn't. So 59, that's a nice example there. So use a computer algebra system. You don't need a computer algebra system. Just calculate this line integral y squared comma x. So number 57, section 6.2. So calculate dr, where c is the parabola x equals 4 minus y squared from minus 5 minus 3 to 0, 2. To 0, 2. So let's take a look at this just so we know what we're talking about. So x equals 4 minus y squared. So that's that leftward facing parabola. From minus 5 through minus 3. So minus 3. So it crosses the y-axis at 2 and minus 2. So it's like right here. Minus 5 minus 3. All the way to 0, 2. Over here. 0, 0, 2. Okay, so, and here the direction of this thing matters. Okay, so we're going from here to here. So we need to pick a parameterization. Well, because x is equal to f of y, or if you had y equal to f of x, so here we pick a parameterization, and we can use a standard parameterization because x is given as a function of y. So standard parameterization here, y is equal to t, x is equal to f of t. For, well, what's the range for t? Right, it's the same as the range for y here. This is minus 3 less than or equal to t less than or equal to 2. Okay, so minus 3 to 2 for y. It's just, you know, the part on the y-axis that you're using to define this part of the curve. So from minus 3 to minus 2. All right, again, you're going to need the derivative, not the length this time, but just the derivative. So minus 2t comma 1. And then you have your vector field, which is y squared comma x. So f of r of t, so you need the vector field along the curve. Y squared is t squared, comma x is 4 minus t squared. Okay. Okay, so now the line integral over c of y squared comma x dot dr is equal to the integral from minus 5 to 2, so what, minus 3 to 2, minus 3 to 2, f of r of t dot r prime of t dt. Okay, that's, the way you do the direct calculation. You just have to calculate this dot product. You end up with a scalar function that you're integrating, and then you go from there. So minus 3 to 2. So f of r of t is this, t squared comma 4 minus t squared dot r prime of t and minus 2t comma 1 dt. Evaluate the dot product, and then it just, reduces to a scalar function. Of course, right, the dot product of two vectors is a scalar. So it's minus 2t to the third plus 4 minus t squared dt. All right, so minus 1/2 t to the fourth plus 4t minus 1/3 t to the third from minus 3 to 2. So minus 16 over 2 plus 8 minus 8/3 minus 3, so 81/2 minus 12, and then at minus 3, so that's plus 27 over 3. So this gives us minus 8 plus 8 minus 8/3 plus 81 over 2 plus 12 minus 27 over 3, which is 9. So that goes away. 12 minus 9 is 3. So 3 minus 8/3 plus 81 over 2. So common denominator here is going to be 6, yeah? So 18 minus 16 plus, this time's 3, so 243 over 6. So 245 over 6. I don't know if that reduces. Is divided by 3? No, it does not. So 245 over 6. Check, make sure we got the right answer there. Which one was it? It was this one, 59. Yeah, 245 over 6. Okay, so, oops. Now notice that you can't apply Green's theorem here because the curve is not closed. Where is it? 59. You can't apply Green's theorem to this because the curve is not closed. Nor can you apply the fundamental theorem of calculus for line integrals because this is not conservative. Okay, so notice the following. Right, Green's theorem doesn't apply. Because curve is not closed. Right, Green's theorem. I mean, sometimes you can like do some trickery in order to get Green's theorem to apply to a non-closed curve by essentially closing it up and subtracting off part of it. But it's not in this one. There doesn't seem to be any sort of like, nice way to do it. Two, the f is not conservative. Because Py is equal to, right, P, where did it go? Py is 2y and Qx is 1. Right, so they're not the same. So fundamental theorem doesn't apply. Okay, so two types of questions there, right? Direct calculation of the scalar line integral, direct calculation of the vector field line integral, in which the vector, neither Green's nor fundamental theorem does apply. So another two types of questions that, we're going to have would be to use the fundamental theorem of calculus for line integrals and Green's theorem, right? So that's 4 questions so far, right? So let's do fundamental theorem. So a third type of question. Right, calculate the line integral over C of f dot dr using the fundamental theorem. Okay, so in chapter or section 6.3, plenty of examples of that. So let's see. Let's do a 3-dimensional example, perhaps. You can find a nice one. No, let's just stick with 2. Um, so 112. Okay, so it's not a great one, but let's see what's Q was just 12y. Derivative of this with respect to y is 12x, and the derivative of this with respect to, no, it doesn't work. No, that one doesn't work either. Oh, come on now. All right, 112. So example. So 6.312. So calculate the line integral over C of, and this one is y comma x dot dr, where C is any. Right, smooth and unbroken curve from 0, 0 to 2, 4. Ugh, I don't like that. From 1, negative 1 to 2, 4. Okay, so there's a couple different approaches to this. Okay, so notice, okay, f is conservative. Right, so because py is 1 and qx is 1. Right, so we can find the potential function. So solution number 1, okay, find fxy for which the gradient fxy is equal to y comma x, right? And then apply the fundamental theorem from there. Okay, so in this case, right, the partial derivative of f with respect to x is going to be y, and the partial derivative of f with respect to y is going to be x. So antiderivative here with respect to x is going to be xy plus some function of x, the arbitrary constant, or some function of y, which is the arbitrary constant when taking the derivative with partial derivative with respect to x. This one, antiderivative with regard to y, xy plus some function just in terms of x. That would be an arbitrary constant when taking a partial derivative with respect to y. So here just let g and h be 0. So we use fxy equal to just xy. Okay, so now by the fundamental theorem, the integral over c of y comma x dot dr is equal to that potential function xy from beginning to end, 1, -1 to 2, 4. So at 2, 4 you get 8, and at 1, -1 you get -1, so 9. So that's solution number 1. Now, solution number 2, another consequence of the fundamental theorem is that the answer is independent of the curve itself. All that matters is where the curve starts and where the curve finishes. So you can calculate the line integral directly by picking a nice curve. A line segment would be, a typical example. So solution number 2. So there was 1, -1 to 2, 4, right? And c goes from here to there. Right? Just use c as a line segment. And the integral value is unchanged because the vector field is conservative. So that is a consequence of the fundamental theorem of calculus for line integrals, is that the line integral is path independent, as they say. Okay, so the vector from here to here is 1, 5. So we're going to pick r of t to be that standard parameterization of the line segment from A to B. So that goes like that. You start at the base point here at the tail, 1 minus 1, and then you add t times the vector from here to there. So plus t plus 5t, 0 less than or equal to t less than or equal to 1. So that's a standard parameterization of a line segment. That always works with t going from 0 to 1, as long as you take the line segment to be the entire vector, not just part of that vector. So r of t is equal to 1 plus t, comma, minus 1 plus 5t. So r prime of t is equal to 1, 5, which turns out to be that slope vector again. F is y comma x. So f of r of t is equal to y is minus 1 plus 5t, x is 1 plus t. So now the line integral over c of f dot dr is equal to the integral from 0 to 1 of minus 1 plus 5t, comma 1 plus t dot r prime of t, which is 1, 5 dt. Doing the dot product here, it's minus 1 plus 5t plus 5 plus 5t dt. So that gives you the integral from 0 to 1, 10t plus 4 dt. Antiderivative, 5t squared plus 4t from 0 to 1. So 5 plus 4 minus 0 is 9. Same answer. And it doesn't matter what curve you picked. And, you know, when it doesn't matter what curve you pick the nicest one, which is typically a line segment. Doesn't have to be. I mean, there could be, you know, for other types of integrals, some other curve that's like quote unquote nicer. I would not recommend doing it this way. I would recommend just using the fundamental theorem, but I don't know, for whatever reason it is, it seems like I get like half the class that does it one way, and half the class that does it the other way. Although it's easier to make a mistake, I think, in this second type of solution. But I mean, you know, you guys are all careful and you double check your details and all that. You know, it shouldn't be a problem. But I think number one is solution one is easier. Takes less work. Now, by the way, this whole path independence stuff is only for conservative vector fields. Like this one that we did earlier, this 245 over 6, this one over the parabola, if you just took the line segment from here to there and calculated it over that, it's not going to be the same. It's not going to give you the 245 over 6. It's going to be something different because it's not conservative. It's not path independent. Okay, and then a fourth type of question, you know, calculate an integral. All right, calculate a line integral using Green's theorem. Okay, excuse me for a second, guys. I just need to step away just from the back. So, calculate a line theorem using Green's theorem. So here's Green's theorem. Okay, so Green's theorem is just in 2 dimensions. And Green's theorem states that the line integral for the vector field p comma q over c, where c is a simple closed curve. So it's a circle that's, you know, deformed, essentially. Right? It's just a closed curve that doesn't intersect itself, where you have an inside and an outside region, oriented counterclockwise. Right? So for such a curve, there's like a well-defined counterclockwise direction. Green's theorem is that line integral is the double integral over the inside of the curve r, partial derivative q with respect to x minus partial derivative p with respect to y, dA. Right? So, for example, in section 6.4, it's about Green's theorem. think we did this one. Well, number 150, didn't even state the question kind of in a good way. 149 we did. Oh, 148 looks, that's not a good example. So, number 155, say, y to the third minus x to the third y squared. So calculate that, where C is the counterclockwise oriented circle of radius 2 centered at the origin. That's number 155. So calculate this, where C is that circle of radius 2 oriented, the whole thing oriented counterclockwise. Okay, so here P is y to the third, Q is minus x to the third y squared. So partial derivative of P with respect to y is 3y squared, and partial derivative of Q with respect to x is minus 3x squared y squared, like that. Okay, so by Green's theorem, the double integral over the inside of C, which is R, the circle of radius 2. So, I mean, before we even get into that, I mean, obviously we're going to have to do some polar coordinates here. So that's 0 less than or equal to R less than or equal to 2, 0 less than or equal to theta less than or equal to 2 pi for the entirety of that disk of radius 2 inside. So double integral over R of qx minus by dA. So it's the double integral over R qx minus 3x squared y squared minus py 3y squared dA. Okay, so that's the double integral we need to calculate. Now, the question is, how are we going to calculate it? Are we going to calculate it with rectangular coordinates, ordinary rectangular coordinates, or do we need to reduce to polar coordinates? Not reduce, but transform to polar coordinates. Well, because you're dealing with, this circle, this disk of radius 2, probably polar coordinates is the way to go here. So this is equal to, so transform to polar coordinates. The double integral 0 to 2, 0 to 2 pi. So that's going to be minus 3. I'll factor out the minus 3. So r to the fourth cosine squared theta, sine squared theta, plus the y squared, r squared, sine squared theta, r, remember when you transform to polar, we have this correction factor of r. So this is minus 3, integral from 0 to 2 pi, integral from 0 to 2, r to the 5th, cosine squared theta, sine squared theta, plus r to the 3rd, sine squared theta, dr d theta. So now let's calculate the antiderivative with respect to r. So 1/6 r to the 6th, cosine squared theta, sine squared theta, plus 1/4 r to the 4th, sine squared theta. For r going from 0 to r going to 2, d theta. So it's equal to minus 3 times integral from 0 to 2 pi. So 2 to the 6th is 64. So 64 over 6, that's 32 over 3. Cosine squared theta, sine squared theta, plus 16 over 4, so it's 4 sine squared theta, d theta. Now this is not the nicest integral to try to calculate, but we can do it here. You have to apply the double angle formula to the cosine squareds and sine squareds. Actually, you're going to end up applying it a couple of times. Well, actually, hold on. Is this... Oh, no, they're not 0 because they're strictly positive functions. 32 over 3. So this becomes 1 plus cosine 2, or 1/2. So 1/2 and 1/2. We're going to get a 1/4 out here. 1 plus cosine 2 theta times 1 minus cosine 2 theta. Plus 2 times 1 minus cosine 2 theta, d theta. So 32 over 4, that's 8. And this is 1 minus cosine squared 2 theta. So you have to apply it again. Plus 2 minus 2 cosine 2 theta. The integral from 0 to 2 pi of cosine 2 theta, that one's 0. So I'm just gonna leave that, just let that go, that term. Okay. All right, we're integrating cosine from 0 to 2 pi. Well, we're integrating cosine x from 0 to 4 for x going from 0 to 4 pi. It's going to be 0. So this one, applying that double angle formula again. So 1 minus 1/2, 1 plus cosine 4 theta, close, plus 2. So let's clean this up. I have 8/3 minus 4. Well, let's distribute that through. So I got 8/3 minus 4/3, 1 plus cosine 4 theta, plus 2. So this becomes 4/3 here. So 8/3 minus 4/3 is 4/3 plus 2. 2 is 6/3. So I got 10/3 minus 4/3 cosine 4 theta, d theta. But that integral again is 0. The cosine 4 theta from 0 to 2 pi. So I just have this 10/3 times 2 pi. is 20 thirds times minus 3. So that's right, minus 3 times 10 thirds times 2 pi. So 20 minus 20 pi. Okay. So, not the, I wouldn't give something that sort of tedious, but for whatever it's worth, there it is. Okay, so so that's an example of Green's theorem. Now, I don't have to throw one at you where you're going to transform into polar coordinates. It may just be something that you do in rectangular coordinates. All right, so that's what? How many questions so far did we cover? All right, types of questions. So there's direct calculation, question number 1. Direct calculation, question number 2. Fundamental theorem of calculus, question number 3. Green's theorem, question number 4. All right, now, for surface integrals, again, 2 types of surface integrals. There's the scalar type, and there's the vector field, the vector flux surface integral. So question 5 and question 6 would be a direct calculation of a scalar and a direct calculation of a vector surface integral. Okay, and the way those are calculated are shown right there. And then, so that's question 4. So 4 questions on line integrals, and then these 2 questions on surface integrals. And then a question to apply Stokes' theorem, and a question to apply the divergence theorem. There's your 8 questions right there. Okay, so 4 questions on line integrals, 4 questions on surface integrals. All right, so first let's do an example of a surface integral, scalar surface integral, just direct calculation. Well, there's no theorems to help with those, so it's always direct. So 5th type of question. So calculate a scalar surface integral. So that's in section 6.6. .285, that's a vector. 286, that's a vector. 287, two G is that. 291. Here's a nice one. So they wrote it in a very opaque fashion, but evaluate the surface integral. So this is xz plus 2x squared minus 3xy. Xz 2x squared minus 3xy. Minus xy. Three xy. Where S is the plane, so calculate this. Where S is the plane 2x minus 3y plus z equals 6 over the square as 0, 1. All right, so you've got this plane. Right, it's here or whatever. I mean, I'm not going to draw it exactly, but the portion of the plane that's over the square. You can't calculate the surface integral over the whole plane because right, I mean it's infinite. You know, you need a finite measure domain over which you're calculating. So here we've got this bit of this bit of the plane that's above the square. Right. So remember we talked about how to restrict just part of the plane, like above a square or above a rectangle in the first octant, that kind of thing. The triangle of a plane that just sits in the first octant, or the part of a plane inside a cylinder. That's another one that they throw at you. Okay, so we have to pick a parameterization here. So this is z equals 6 minus 2x plus 3y. So because it's a surface z equals f of xy, you can pick your parameterization. Standard parameterization, r, x, y. X is x, y is y, and z is fxy. Now you need your partial derivatives of r with respect to x and y. Uh, 0, 1, 3, like that. And then you need the cross product. And here it doesn't matter which order you do the cross product in, because it's a scalar surface integral. I, j, k, 1, 0, minus 2, 0, 1, 3. So this cross product is 1. And then here it's minus 3. And here it's, again, 1. And the j coordinate, it's 3 minus 0, so it's minus 3. So then the length of our x cross our y is equal to square root 1 plus 9 plus 1 is square root 11. All right, and then we have our function f x, y, z. It's always going to be a three-dimensional function because the surface has to sit in 3 dimensions. And that's this. And then you need f along r of x, y. So x is x and z is, what was it? 6 minus 2x plus 3y. So plus 2x squared minus 3xy. So let's do this. Minus 2x squared plus 3xy plus 2x squared is 3x. Y, so that's why the function is so funny looking. So you just get 6x. All right, so now the surface integral of this over S surface integral over S of that is the double integral over R. Okay, and that's the little square in this example. F of r of x, y times the length rx cross r, y, t, a. So the surface integral reduces to just a double integral. So that's the double integral over r, and this was 6x, this was square root 11 dA. So it's just 6 square root 11. R was that rectangle, 0, 1 to 0, 1, x dx dy. So 6 root 11, and go from 0 to 1, a half x squared from 0 to 1 dy. So this is a half. So this is just, this integral is just 1. So 3 root 11. Oops, root 11. I'm sure that's right, but let's double check. It's 3 root 4. 3 root 4. I think it's 3 root 11. xz plus 2x squared minus 3, that was right. So it's 2x minus 3y plus z equals 6. So z is 6 minus 2x plus 3y. So partial derivative of r with respect to x, partial derivative of r with respect to y. So this is, here it is. No. Calculate one of these Oh, this first determinant is 2, not 1, 2. So that's 4. So this is root 14. Root 14. Is that what the answer was in the back? I think they mean 14 because root 4 is equal to 2. And this is right. Okay, so so that is, an example of the scalar surface integral. Now, how about an example of a direct calculation of the vector surface integral? So they're using hemisphere, portion of the plane. Let's not use that. Let's do on 285. So x is x, y is y, and S is the hemisphere, the upper hemisphere of the sphere of radius 1. So number 285, so that's a 6th type of question. All right, calculate directly a surface vector flux surface integral. So 285 so F is equal to x is x, y is y, z is 0. So calculate, right, and s is equal to the sphere of radius 1, just the top half, oriented upwards. Of radius 1, top half. Okay, so again, you need to pick a parameterization. So again, because we have the surface given by z equals fxy, we can pick a standard parameterization. So x is x, y is y, and z is this. And then we need partial derivatives of r with respect to x. Partial derivative of r with respect to y. And Rx points in this direction and Ry points in that direction. So the cross product, using the right-hand rule, the cross product that you want to correspond to the upward orientation of that surface is Rx cross Ry rather than Ry cross Rx. So that's I, J, K, 1, 0, 0, 1, like that. So this cross product is equal to x over square root 1 minus x squared minus y squared. And then in the j component, it's negative of that, but then you negate it. And then in the z component, you just get 1. K component, you just get 1. So that's Rx cross Ry. So now, we want to, calculate the surface integral f dot ds over s. Okay, so, they say s, or sometimes they write it like this, f dot n, which is the normal vector, unit normal vector, ds for ordinary surface integral, but that's just the way it's defined. Okay, so there's different notations that go along with it. I will use this one. That's the one I usually use. So now the surface integral, vector flux surface integral, xy0 dot ds is equal to the double integral, okay, over r, which is the region defining this disk, or this sphere, which is going to be the disk of radius 1. Right, so that's going to be the region R for x, y. So the double integral over R, f of R of x, y, dot Rx cross Ry dA. So f of R of xy, well, f was what? It was xy0, so f of R of xy. Well, in the standard parameterization, x is x and y is y, and 0 is fxy, or z is fxy, but there's no z's there, so you don't have to worry about it. So this one is just xy0 dot, this thing here, x over square root 1 minus x squared minus y squared, y over square root 1 minus x squared minus y squared, 1 dA. So this is equal to the double integral over r x squared plus y squared over square root 1 minus x squared minus y squared dA. So this should be done in polar coordinates, right? Transform to polar coordinates. Oh, but it's still a nasty one. Requires a trigonometric substitution. So it's the disk of radius 1. So this is r squared, square root 1 minus r squared, r dr d theta. So it's integral from 0 to 2 pi r to the third over... So that requires a trigonometric substitution, which I'm not going to do. So integral antiderivative x to the third divided by 1 minus x squared to the 0.5. So that is minus 1/3 square root 1 minus x squared. So let me do the theta first, actually. I lost my theta, didn't I? So let's do d theta dr 0 to 2 pi, integral from 0 to 1. So there's no thetas here, so it's just 2 pi. So it's minus 2 pi over 3. There we go. Well, square root 1 minus x squared. R squared plus 2. From 0 to 1. So at 1, this is 0, right? Because that's just a 0 there. And then at 0, this is the square root of 1 times 2. So 4 pi over 3. Right, and if you wanted to do this, calculate this antiderivative. So the antiderivative is calculated using r equals sine of theta. So it's a trigonometric substitution, which I'm certainly not going to throw at you on the exam tomorrow. All right, but I mean, this is a straight calculation of a vector flux surface integral. And notice that, it's an open surface, right? It's got the surface with boundary, but Stokes' theorem doesn't apply here. Stokes' theorem doesn't apply here because Stokes' theorem is where you end up evaluating the not double integral, not the surface integral of f, but the surface integral of the curl of f. Right? That's where you replace the line integral with the surface integral of the curl. So let's do an example for that. So we actually did not go over everything in that section. So let me grab the syllabus and go over some more of those in this last time that we have here. So that was a fifth type of fifth and sixth. Did I say sixth? Yeah. Seventh type of question. Apply Stokes' theorem. sometimes called the curl theorem, and that's it right there, right? That the line integral of f dot dr is the surface integral of the curl of f dot ds, where C is the clockwise orientation. Sorry, not the clockwise. The right hand orientation of the boundary of surface S. Right, so surface S is oriented from boundary 1 or from side 1 to side 2. And C is oriented according to the right hand rule, the boundary of the surface S. If you slide the fingers of, oh, look at this. But unfortunately, that is turned 90 degrees. So take this hand and turn it 90 degrees. If you slide the fingers of this right hand along the curve, then the thumb points in the general direction upward. So that's the correct orientation that goes along with this upward orientation of the surface. Okay? So the line integral of f dot dr over the boundary of the surface is the surface integral of the curl of f dot ds. And the thing to remember about Stokes' theorem is that it's not the surface that matters, it's the boundary of the surface that matters. Whatever surface it is that you pick, as long as it has boundary C, you're good to go. So typically, you pick a plane, some real easy surface to work with. So Stokes' theorem, 13.6.7. So let's do, say, number 353, 351. Let's see. Excuse me. Use Stokes' theorem to evaluate the line integral f dot ds, where this is f, and C is the triangle with vertices 0, 0, 0, 2, 0, 0, and 0, negative 2, 2, oriented clockwise when viewed from above. So 353. So 6.7, number 353. So calculate f dot dr over C, where C is this. So 0, 0, 0, 2, 0, 0. And 0, negative 2, 2. So we're going from here, oriented counterclockwise when viewed from above. So when viewed from above, counterclockwise is that way. Okay, so that is C. Now, the surface that you want to pick would be the easiest surface to deal with that has that boundary. So in this case, it's just going to be the plane. So apply Stokes' theorem that, oh, what was F? I'm sorry. YZX. Right? So apply Stokes' theorem. So the Stokes' theorem is that f dot dr over C is equal to the surface integral over S of the curl of f dot ds. And let's pick S to be the plane defined by this triangle. Okay, how can we get the plane defined by this triangle? Different ways to do it, different ways to go about doing it. This one actually is I think pretty easy to just see it. It didn't quite. So this is y, z, x. Maybe if I kind of do it, maybe it looks a little better. What's this line right here? What's that line? That's the line z equals minus y. So this is the plane z equals minus y. Right? So the equation of the plane z equals minus y. X doesn't appear in the equation there. It's just z equals minus y. Right? That's the line z equals minus y right there. Z equals minus y right here. And it's just extended in the x direction. That's the plane. But what's the domain? Right? So your standard parameterization, x is x, y is y, and z is fxy. But what's the domain for x and y? Right, this is the point -2 for y, and this is 2 for x. This is the domain, R, down here. Right, it's the projection of that surface, it's the shadow of that surface in the xy plane when you shine the light straight down. Right, so the surface we're using is this plane. The domain for it is that triangle down there, and of course we want to be oriented in the upward direction there. All right, so the domain region over which this is defined is right here. So this is the x-axis here. And then the y-axis, this orientation of it is giving me kind of a hard time. So -2, 2. So that's R right there. Right, so this is 0 less than or equal to x less than or equal to 2. And then the y, so right, x going from 0 to 2, y goes from this line to here. Right, so y goes from this line to here. And what's this line right there? Right, it's got slope 1, right, and y-intercept -2. So x -2. Right, so that's a type 1 description for R, right? That's the line y equals x -2. Slope is 1, y-intercept is -2. Okay, so we've got the surface now. We've got this curve C, right? And then we found a surface. Doesn't matter what the surface is, just matters what the boundary of that surface is. We did a lot of examples like that last time, right? Where essentially we always picked a plane, right? I mean, they gave you a surface whose boundary was this circle, and then the surface was like a sphere or this paraboloid or whatever else it was, but it doesn't matter. You can just re-choose the surface. That's what Stokes' theorem says. That the surface integral of the curl is the line integral over f on the boundary. Well, the boundary is what matters, not the surface. So any surface that has that boundary will work, and the value of this won't change. Okay, so partial of r with respect to x, in this case, is 1, 0, 0. Partial of r with respect to y is 0, 1, -1. Partial of r with respect to x is in this direction, or y is in that direction. With respect to x is in that direction of the x-axis. So we want rx cross ry rather than ry cross rx. I, j, k. 1, 0, 0, 0, 1, minus 1. So this is equal to 0 in the x-coordinate, 1 in the y-coordinate, and 1 in the j-coordinate, or z-coordinate. So that's the Rx cross Ry that we're going to need. Now, the curl, right, so the vector field F was equal to y, z, x. So now the curl of F, right, is the 3 by 3 determinant, ijk, partial with respect to x, partial with respect to y, partial with respect to z, y, z, x. So this is equal to, in the x-coordinate, it's this partial minus that partial. They're both 0. In the j-coordinate, it's this partial, which is 1, minus that partial, which is 0, negated. And in the k-coordinate, it is this partial minus that partial, which is minus 1. So this is the curl of f dot ds, which is equal to the double integral over r, the curl of f along r, along the parameterization, dot rx cross ry, dA. So this is equal to double integral over r, and these turned out to be just constant, right? It's 0, -1, -1, dot, and this last one was just 0, 1, 1, dA. Oh man, this is a constant, right? So it's minus 2 over r. So well, I mean, we didn't even need to get r. So it's minus 2 times the area of r. Right, in this case, it's minus 2 times the area of this thing is 1/2 the base times the height of that right triangle, so it's 2. So minus 4. Okay, no actual calculation actually happening there. Where's that problem? So that was this one. Let's check it real quick. Make sure we didn't. That was 353. Yeah, minus 4. Right there. Right, so now, of course, you didn't need to do Stokes' theorem with that. You could have just calculated that thing manually, that line integral manually, although that really would have been a pain because you would have to parameterize that triangle, which would necessitate using 3 separate line segments. You'd have to parameterize 3 separate line segments and calculate that line integral 3 times over those 3 line segments and then add it up. So, I mean, you save quite a bit of work in doing Stokes' theorem there. All right. Oh, 54. Around C, which is the intersection of the cylinder and the hemisphere. Check out 354, by the way. I'm not going to do it, but let's just talk about it. Okay, so in 354, they're saying use the surface integral in Stokes' theorem to calculate the circulation. So it's the vector field line integral f x y z x squared y to the third comma 1 comma z around C. where C is the intersection of the cylinder of radius 2. So there's the picture right there. X squared plus y squared equals 4. And the half sphere, x squared plus of radius 4. X squared plus y squared plus z squared equals 16. Oriented counterclockwise when viewed from above. What surface would you pick? So this blue circle is the curve. So what surface would you pick that has that blue circle as a curve? You don't have to pick the hemisphere. I mean, that hemisphere is describing the intersection. Is used to describe the intersection of this of the cylinder and the hemisphere there to define C. You could pick it to be the surface because that little cap on the sphere, has C as its boundary. But there's no point in doing that. You might as well just pick the disk. The disk that has C as its boundary, and that disk is just X is equal to X, Y is equal to Y, and Z is equal to something. Z is equal to the square root of 12. So Z is the square root of 12. X is X, Y is Y, Z is square root of 12. So that's the surface you would use, right? Instead of that hemisphere. Okay. So the last type of question is divergence theorem. Okay? Divergence theorem is when you have a closed surface, right? Simple closed surface, meaning the surface is not self-intersecting. It's a deformed sphere. It's like a cube or tetrahedron or just a potato shape of some sort. It's just a surface with an inside and an outside. Okay, as long as you have continuous partial derivatives inside the surface, inside and on the surface, the vector flux integral from inside out. So the flux of vector field coming out from inside to out of that surface, that's the surface integral f dot ds, is the triple integral of the divergence of f over the interior of s. It's a real simple statement. It's simpler to deal with than Stokes' theorem. Because you don't have to calculate any weird cross products and anything like that anymore. So let's do some example from section 6.8. So let's see, 397 is one of the problems. I want to do a sphere calculation. 402, 410. All right, 402, real simple. So in 402, so calculate f dot ds, where f is this right here. So 8th type of question. EIGHT8. So apply Stokes' or divergence theorem. So 402. So calculate f dot ds, where f is equal to 2x minus 3xy xz squared, where s is the cube oriented outwards. Which cube? This cube. So 1, 1, 1. So it's the cube who going from 0 to 1, 0 to 1, 0 to 1. So this is 1, 1, 1 right here, down like that. So oriented outwards. Now, if you were to try to calculate that manually, you would have to, parameterize the 6 sides of the cube, so like we were talking about before. Okay, so by the divergence theorem, so this is f is 2x minus 3xy comma xz squared. The divergence of f is equal to the derivative of this is p, q, and r, the derivative of p with respect to x, plus the derivative of q with respect to y, plus partial derivative of r with respect to z. So this is 2 minus 3x plus 2xz. Right, so the surface integral of f dot ds is equal to, by the divergence theorem, the triple integral of the divergence of f dv over the inside of the surface. Right, so much easier to conceptualize kind of theorem here. I mean, the surface defines R itself, just looking at it. So in this case, it's integral from 0 to 1, 0 to 1, 0 to 1, 2 minus 3x plus 2xz dy dz dx. Because everything's a constant there, you can do it in whatever order you want. So there's no y's there, so it's just that constant times 1. So 2 minus 3x plus 2xz dz dx. So antiderivative with respect to z, 2 minus 3x times z plus xz squared from z equals 0 to z equals 1, and then dx. So this becomes integral from 0 to 1, 2 minus 3x plus x dx. So integral from 0 to 1, 2 minus 2x. So that's 2x minus x squared from 0 to 1. 2 minus 1 is 1. All right? So, that's a nice example of the divergence theorem. Other examples of the divergence theorem, what types of closed surfaces are sort of, standard things that you might see. I mean, cubes are one thing. Another thing that you would get is a sphere. I mean, a nice closed surface, that you would work with is the sphere. And there's several questions in here that deal with the sphere. 410? No. 397, I think, did. Yeah. So here we got the sphere of radius 2. So let's look at 397. And here is F. So in 397, so F is equal to y minus 2x, x to the third minus y, and y squared minus z. And then S is the sphere of radius 2 oriented outwards. calculate, the surface integral f dot ds. Calculate over s. Okay, so using Stokes' theorem, so let's calculate that divergence first. So this is P, Q, and R. The divergence of F is the partial derivative of P with respect to X, plus partial derivative of Q with respect to Y, plus partial derivative of R with respect to Z. So in this case, we have minus 2, Q minus 1, R minus 1 again, so minus 4. So by Stokes' divergence theorem, triple integral over the inside of the surface, the inside of the sphere, divergence of f dv. So it's triple integral over the sphere, and this is just minus 4 dv. So it's minus 4 times the volume. Because it's a constant, it's minus 4 times the volume of R. So minus 4 times, and that's the sphere of radius 2. So 4 pi. Or, no, sorry. The circle. The radius of the volume of a sphere, just in case you didn't know. So the volume of the sphere is 4/3 pi r to the third, where r is the radius. So this is radius 2. So this is 4/3 pi times 8. So what do we got here? 8 times 16, so it's 3, 4, 5, 6, 7, 128. Okay, now, if it wasn't a constant, you could conceivably calculate using spherical coordinates. Still check the answer there. Yeah, minus 128 pi over 3. So if it wasn't, so note, if the divergence of f was not a constant, it might be necessary to use, spherical coordinates to calculate. Or cylindrical. If it was, a different type of surface that, where cylindrical coordinates might be appropriate. Okay. So there you go. That's the 8 questions you're going to have. 8 types of questions. All right, and the summary, yeah, it outlines all of that. So 1, 2, 3, 4, 5, 6, 7, 8. All right, and this is on the website. So I gave you the link. I'll send it to you again after class. Let's take a few minutes, guys. 5 minutes. I have to step away for a few minutes, and we'll be right back. Okay. Questions, guys. Does anyone have questions? Is unclear about what's going to be on the exam, what to study. Let me think, guys. What questions about where we're going, what we're doing here? What type of questions? Let's uh, let's do another type of let's do another couple example surface integral type question. You know, so here is a okay. Let's let f be equal to. Now I can't just pick any old thing. Off the top of my head, what can I choose? Just pick something and hopefully it goes okay. Well, let's do x, z, z. So we'll just say x, z, z. All right, let f be equal to this, okay? So f is x, z, z, and s is the upward-oriented surface z equal to 1 minus y squared above the rectangle 0 less than or equal to x less than or equal to 2, 0 less than or equal to y less than or equal to 1. Calculate f dot ds. Okay, well, this is just a straight vector flux surface calculation. Okay, vector flux surface integral calculation. So here's the surface. Right, z equals 1 minus y squared for y going from 0 to 1. Of course, that's just the parabola facing down. Right? And because x isn't in the equation, we use the cylindrical construction where we just copy the curve in the yz plane and extend it in the x direction. Like that. So this is the surface. All the way down to x equals 2. And it's oriented up. Okay, well, in order to calculate this, we need to parameterize the surface. Okay, well, we can do a standard parameterization, r, x, y, where x is x, y is y, and z is fxy. Now we need those partial derivatives. And partial of r with respect to y looks like that. And, partial of r with respect to x when you're doing a standard parameterization, and the partial of r with respect to y, they're in the direction of the x and y axes. So the cross product you're looking for is rx cross ry. 1, 0, 0, 0, 1 minus 2y So this is equal to, in the x-coordinate you have 1, in the y-coordinate you've got minus 2y, negated is 2y, and in the k-coordinate you just got 1. Okay, so so that's the cross product. So now the surface integral xzz dot ds is equal to the double integral over r, and r is just this rectangle here. It's the part of the surface that's above that rectangle. Right? So that's my domain r for the standard parameterization, is the shadow of that surface in the xy plane. So double integral over r, xzz. Well, let me write it out. So it's f of r of xy dot rx cross ry dA. So this is equal to the double integral over r, xzz. So x is x and z is 1 minus y squared. Dot this, 1, 2y, 1 dA. So it's the double integral over r, x plus 2y times 1 minus y squared plus 1 minus y squared dA. So this is equal to double integral over r, so x times plus, so it's 2y minus 2y to the third plus 1 minus y squared dA. So double integral, so let's iterate. So x goes from 0 to 2, y goes from 0 to 1. So x minus 2y to the third minus y squared plus 2y plus 1 dA. Or let's do dx dy. Right, the 2 is for the x, not the y. Well, the antiderivative of the x from 0 to 1, this is going to be a half. And then this is just going to be that back. So it's 1 half minus 2y to the third minus y squared plus 2y plus 1. And no, it's not a half, sorry. 1 half x squared, 0 to 2, so it's force 2. Base is 2, height is 2, right, it's 2. So 0 to 1, so that just becomes a 3 over here. So we've got, let's see, minus a half y to the fourth minus a third y squared, or y to the third, plus y squared plus 3y from 0 to 1. So minus 1 half minus 1 third plus 1 plus 3. Common denominator, well, so that is 5/6. So 4 minus 5 over 6 is 24, so 19 over 6, right? Yeah, 6 times 4 is 24, minus 5 is 19. All right, so there's another nice example of a straight calculation of a surface integral, vector flux surface integral. Okay, so questions, guys? That's all I've got for us today. Okay, so we'll end it at that tonight, and you know, I'm in my WebEx room tomorrow and Wednesday from 12:30 to 1:30. So you know, I'll send you a reminder about that. And other than that, email me any questions or concerns. And other than that, make sure your webcam's working, and we'll see you on Wednesday. Okay. All right, guys. Have a good night.